Well, good evening, everyone. Welcome to the Carnegie Institution for Science. It's a pleasure to have you all here tonight, and it's great to see a full auditorium. I'm Andrew Benson. I'm a scientist here at the Carnegie Institution, working in the field of astrophysics. And it's our honor tonight to co-host this event with the Coverley Foundation, the Royal Embassy of Norway, and the Norwegian Academy of Science and Letters. And so I'd like to begin by inviting the president of the Norwegian Academy, Hans Petter Grave, to give a few remarks. He's here tonight on behalf of the Coverley Foundation.
Thank you. Coverley Laureate Linde, Ambassador, ladies and gentlemen. Today we are here to listen to a lecture by a Coverley Laureate, and to give you some information about the Coverley Prize, here's a short film.
What if we could understand the origin of the universe? What if we could improve lives by controlling atomic structures? What if we could truly grasp the complexities of the human brain? The story behind the Coverley Prize started in the 1930s with a curious boy named Fred, growing up among the tall mountains of Ellisfjord in Norway. A deep curiosity about nature and the universe stayed with Fred throughout his studies in physics and his entrepreneurial success in the United States. Until he eventually established a philanthropic foundation with the vision of advancing science for the benefit of humanity. One of the first activities of this foundation led to the inauguration of the Coverley Prizes, beginning in 2008. The prizes are awarded every 2 years in a partnership between the Coverley Foundation, the Norwegian Academy of Science and Letters, and the Norwegian Ministry of Education and Research. Each of 3 international prize awards consists of $1 million and a gold medal received in a ceremony in Oslo, presided over by a member of the Norwegian royal family. The Coverley Prize laureates are selected by the Norwegian Academy of Science and Letters, based on recommendations from prize committees, comprised of leading international scientists from 6 of the world's most renowned science societies and academies, in the 3 scientific fields: astrophysics, nanoscience, and neuroscience. The biggest, the smallest, and the most complex. The Coverley Prize has 4 ultimate purposes: to recognize outstanding scientific research, honor highly creative scientists, promote public understanding of and appreciation for scientists and their work, and to foster international cooperation among scientists. Time and time again, we have seen that achieving these goals has been critical to making this world a better place. The Coverley Prize continues to be driven by the same sense of awe and curiosity felt by Fred Coverley as he grew up in the midst of nature at its most sublime, experiencing the vastness of the universe.
It's a great pleasure for me to bring greetings to you all from Norway and from the Norwegian Academy of Science and Letters. Andrei Linde was awarded the Coverley Prize in 2014 in astrophysics, together with Alan Guth and Alexei Starobinsky. Here's the proof that he is actually a Coverley laureate, so we're not faking you. The prize was awarded by His Majesty King Harald of Norway in a ceremony in Oslo during the Coverley week. One of the experiences that the Coverley laureates get is to converse with the king. And here's a picture from last year's award ceremony. You see the king in the middle and the laureates of 2018. The awards are celebrated in a ceremony, in a banquet held by the Norwegian government in the Oslo City Hall. They're also greeted, the American laureates are also greeted by the US president. And here you see the picture from the event in 2014. The partners in the Coverley Prize are the Norwegian Academy, the Norwegian Ministry of Research and Education, and the Coverley Foundation. The ministry is represented here tonight by the Norwegian Embassy in Washington. I give the word now to the Norwegian Ambassador, Coverley, please.
So good evening, and as you heard from Hans-Petter Graver, my name is Kåre Aas, and I'm the Norwegian Ambassador to the United States. And it's an honor to be here this evening, and a pleasure to welcome all of you to the 2019 Coverley Prize lecturate by Dr. Andrei Linde, Universe or Multiverse. I had the pleasure of meeting Andrei back in 2014. He had already received the Coverley Prize from King Harald earlier in the year, as we saw here on the screen. And I also had the pleasure to be with Andrei Linde at the White House. I was in the middle of that photo among all the scientists. I'm not the scientist, I was the ambassador. But I must say that I remember that meeting Andrei Linde and his colleague had with President Obama as one of the most important events I have attended during my 6 years here in the United States. And I must say that during that meeting, you could really see the high value President Obama placed on science, and it was really inspiring to see. The contributions of astronomy to our daily lives are many. For example, optics and technology transfer have given us the technology to make cell phones and to take pictures that we can post on Twitter. I'm very good on selfies. So in a sense, you can say that, for better or worse, astronomy helped us give us the selfie. However, astronomy is more than applied science. Technological advances allow us to observe the cosmos in new ways. And what we've seen has provided unique perspectives that extends our horizons and helps us discover the grandeur of the universe and our place within it. I'm looking forward to lecture by Dr. Linde and the moderated discussions to follow. The Norwegian government highly values its collaboration with the Coverley Prizes and the three-way partnership between the Coverley Foundation, the Norwegian Ministry of Education and Research, and the Norwegian Academy of Science and Letters, as well as the long-standing and close ties between Norwegian and American scientists and academic institutions. And we welcome even more collaboration in the future. I'd like to thank the Carnegie Institution for hosting the annual Coverley Prize Laureate Lecture. It is an outstanding tradition that the Embassy very much appreciates and looks forward to every year. The Coverley Prize laureate lectures celebrate great minds and are an essential contribution to science, communication, and bringing science to the public. Along those lines, Dr. Linde, I look forward to being further enlightened on your discoveries related to the creation of the universe. Thank you very, very much for your attention.
So I'm sure that many of you are familiar with the Big Bang, a theory of cosmic origin and expansion that is now nearly 100 years old. But perhaps many of us are not as familiar with the somewhat newer and related theory of cosmic inflation, which explains the exponential nature of that expansion. Consistent with many variations of the exponential expansion theory is the concept that ours was not the only universe that bubbled out of the Big Bang, that other parallel universes also emerged. This might sound like science fiction, but the concept of the multiverse is real science, and as our guest tonight will tell us, there is strong evidence supporting it. Dr. Andrei Linde, one of the pioneers of inflationary cosmology, first proposed a multiverse in 1982. He has worked on the theory ever since, joined by an increasing cadre of like-minded physicists. Today, the inflationary multiverse concept is, according to many, the only robust mechanism that solves all major cosmological problems associated with the origin of our universe. A native of Russia, Dr. Linde received his PhD from the Lebedev Physical Institute in Moscow, after which he became a staff member at CERN in Switzerland. He moved to Stanford University in 1990 to become a professor of physics. His work has encompassed many aspects related to inflationary theory, including cosmological phase transitions, dark energy, global structure, elementary particle properties, and quantum cosmology. He is a member of the National Academy of Sciences, the American Academy of Arts and Science, and the Norwegian Academy of Science and Letters. His many awards include the Dirac Medal in 2002, the Peter Gruber Prize in 2004, the Humboldt Research Award in 2004, the Fundamental Physics Prize in 2012, and in 2014, the Coverley Prize, which he received with fellow physicists Alan Guth and Alexei Starobinsky. It is that last award that we celebrate here tonight. In the citation for the Coverley Prize, Dr. Linde was credited with having developed ever more sophisticated models of cosmic inflation, which dominate current thinking in the field today. Dr. Linde will give us an overview of his work, and then Frank Cesno will join him for a deeper discussion of the topic. Cesno is director of the School of Media and Public Affairs at the George Washington University. He is an Emmy award-winning journalist and creator of Planet Forward, a user-driven web and television project that highlights innovations in sustainability. His journalism career included more than 20 years at CNN, where he served as White House correspondent, anchor, and Washington bureau chief. Along with our co-hosts, the Coverley Foundation, the Royal Embassy of Norway, and the Norwegian Academy of Science and Letters, we are thrilled to honor Dr. Linde as our Spring Coverley Laureate Lecturer, and to have Cesno here to help us celebrate his achievements. Ladies and gentlemen, please join me in welcoming Dr. Andrei Linde.
Oops. Just a sec. Okay, here's mine. Okay, so first of all, I'm really greatly pleased to give a lecture here and to see my old friends and hopefully new ones. The lecture today will be, well, relatively short in comparison to the lectures which I'm typically giving at Stanford University. So they forced me to cut all the equations out and to understand how to present all of this stuff, the best thing which I was able to do first to check Google what people think about a multiverse. And not just Google, but something which is called Google Trends. So what does it mean, Google Trends? Google Trends, special part of it, you really must Google Trends to come there. And then when you go there, you may check a word which you want to check how popular it is and now how many people are interested. I started with checking the universe, okay? And I found, to my dismay, that the interest to the universe steadily falls down. And it was disappointing because, yeah, well, I kind of study universe, but then I've seen several sharp peaks like that, boom, boom. And I thought, oh, wow, this is probably launch of the Planck satellite. And this is, I was too surprised. It was a Miss Universe from Brazil. Then I decided to check multiverse, and what do I see? I see that actually the trend steadily grows up. So interest to the multiverse grows up. And I thought, oh, okay, my work really helps. Then I decided to check, because, you know, I'm a careful person making statistics based on this. So who asked questions about multiverse? Mostly people from Peru, from France, Chile, Argentina, Ecuador, Mexico. Where is the United States? Nobody cares about the multiverse? And then I decided to double check it. What is the origin of that? So most of the questions about Dragon multiverse, Dragon Ball multiverse, the multiverse, Family Guy multiverse. So I thought that let me try to tell Andrei Linde multiverse then. Okay. So let me start with something which bothered us a little bit before, but because we knew that it's impossible to answer this question, it was ignored. Physical constants. This is electromagnetic coupling constant divided by 4 pi, called alpha, and it is equal to magic number 1 divided by 137. And nobody knows why 137. One of my friends was living in the apartment 137. He was a physicist. He thought that he's blessed. But why this number? Alpha, this parameter, is known with accuracy better than 1 in a billion. It is known that it is the same in all parts of the universe with this accuracy. It is at present changes less than this number per year, which means nobody has seen it changing. Okay. So it's a true constant. Looks like a real constant, by why this weird number? And then we open Wikipedia. This is the way how we're learning. Okay? The anthropic principle is a controversial, okay, this is me. Controversial argument of why the fine structure constant has the value it does. Stable matter and therefore life and intelligent being could not exist if its value were much different. And here is explanation. If alpha changes, you die this way. If changes a different way, you die a different way. But then who cares? Alpha is given, okay? So why anthropic principle is controversial? So this argument, at first glance, does not make any sense. We live in one universe with one value of coupling constant. It's measured that it is everywhere constant, as far as we can see, okay? Then this belonging to Albert Einstein. And that is something which everybody took with utmost attention. In his autobiographic notes, not long before his death, he was writing, kind of summarizing his wisdom. And he said this: I would like to state a theorem which at present cannot be based on anything more than a faith. Oh my God, I'm reading a theorem based by but that's Einstein. Okay? In the simplicity and intelligibility of nature, there are no arbitrary constants. Only rationally completely determined constants occur. So the idea was that in the end, if we are good physicists, then we will find the reason why the constants are the way they are, why they cannot be any other way, and that's it. Okay? So this is the principle. This was called the dream of final theory, and we all were his grandchildren. We are trying to follow the dream of our grandfather because he was a genius. We are much smaller scale. So let's just try to do it, and we're trying to do it. And here comes inflation. This is our approach to universe, and inflationary theory actually helped to understand why the universe in different parts is so similar to each other. So this is how people thinking about Big Bang. The Big Bang, the beginning of everything, maybe it is exactly the moment when inflation began. Maybe there was something else before, but we really do not need it to understand what happens later. Then inflation, boom, I will tell you what it is. Okay? And then all normal stuff was created, and then satellites flying. This Coverley Prize was given to these three men, and this man will still await his prize, I hope, because he explained how all galaxies can be created from quantum fluctuations. Equally crazy to what I'm going to tell you. Okay? Oops, just a second. Back. Okay. So this is how, according to inflationary theory, the baby-born universe looked like. It could be as small as this. It could have a size equal to this. Why this number? Because according to quantum gravity, if you consider anything with scale smaller than this, then space and time fluctuates on this scale so strongly that your rulers will instantly bend. You cannot measure anything there. Mass 10 to the minus 5 grams. You take the smallest scale, you can put there matter. You cannot put there more than that, otherwise it instantly collapses. So then suppose that we take small piece of space and let inflation do its work. And what is inflation? I will tell you a little bit later. But if it works, okay, let me start with that. So here is a magic trick. It is totally insane. And that is why it really, I hope, helped me that all of this introduction and prizes, etc. So maybe this is not total nonsense. Because if I would be given a chance to show you my equations, but then it would be clear. But since I don't, so here is the idea. Okay. Suppose you have a box of candy. Okay. In expanding universe, box of candies expands. So here is a box, 1,000 candies there. Universe expands, how many candies there? Same 1,000 candies there, right? Okay? Number of candies is conserved. That was the idea of the Big Bang story. You have a given amount of photons, protons, everything together. The number is approximately conserved with expansion of the universe. And then how many do you need to start with? Well, to create our universe, you need to have approximately 10 to the degree 80 tons of matter. Like that. Big miracle, okay? So what we can do right now, we can do a magic trick. Without magic trick, nothing works. So you have a box filled with heavy nothing. Okay? Okay, yeah, here we start. Okay. Heavy nothing, which means you have energetic vacuum with energy density, energy per cubic centimeter. Okay? It is not a joke, it is a reality, because when we see empty space, it does not mean that it's actually empty. In '98, people have made a Nobel Prize winning discovery that empty space in our part of the universe right now has non-zero vacuum energy, called cosmological constant, or maybe quintessence, or maybe whatever. So this is something which look like empty space but has some energy. And in quantum field theory, it's quite possible that the universe initially had a larger energy, especially if it was filled with something which is called scalar field, and it is also a concept which I was forbidden to use. Okay? But the scalar field is like a heavy vacuum. Our universe expands, and the scalar field remains approximately the same. Expands, and it remains the same. Expands, so you start with a box filled with scalar field. What's inside? Nothing, okay? You make it 10 times more. What is inside? Nothing. The same nothing, but 1,000 times more of it. 10 by 10 by 10. Then it continues expanding. What you get there? Nothing. but energy density per cubic meter is the same. It is this special nothing, okay? And then it decays. Each cubic meter produces you 1,000 candies, but now you have exponentially many cubic meters. You produce all candies for all kids in the universe, okay? That's the basic idea of inflation, okay? Does it sound like cheating? Yes, yes, yes. Okay, give me more equations. But okay, I will tell you one way of resolve the problem. No. Oh, okay, the thing is that the thing is that the total energy of the universe is exactly equal to 0. That is the true statement, true to God. Okay, you have energy of matter, and you have energy of gravity. Okay, the total energy is conserved. If you have a hot expanding universe filled with photons, the universe expands. Photons make job expanding the universe, and they lose energy. The universe filled with photons, which is a Big Bang story, the photons lose energy, and so they become red, infrared, cosmic microwave background radiation, radio waves, the same universe, but the energy is lost. So the idea was that how to find a mechanism where energy not lost, but excavated. And the idea that you have this 0 energy of everything, and it's split into energy of matter and energy of gravity, energy of metric. And if this happens fast, then you have exponentially large energy of matter, exponentially large negative energy of gravity. So this is a special regime where expansion, instead of taking energy of something, in this case, this scalar field, okay, then it gives its energy. And if you write equations, you see that there is no cheating. The same Einstein equations, the same equation for scalar field. They're as simple as equations for harmonic oscillator. And trust me, I preserved them for everybody who wants to see in the end of my lecture after it's over. Okay? So I'm just saying that it is doable. It is not like really total cheating. It looks like cheating. What is cheating if you say that this is a vacuum, heavy vacuum? Because when vacuum expands, then how do you know that it is expanding because there is nothing? It's okay. So that is the cheating. And therefore, the first versions of the theory did not quite work. And then, well, I invented the new versions, and they start working because it was not completely vacuum. So all of these subtleties aside, this is the basic idea. Okay? Basic idea that you start with something small, and then you wait 10 to the minus 35 seconds, and the universe becomes like that big, okay? Maybe I've written an extra 0. I don't know. It depends on the model of elementary particles. Maybe 2. Maybe I did not write enough. In fact, if you study theory of eternal inflation, then the number must be much greater. What is important that it's in any units of length, okay? Because it's centimeters. In meters, there is a, well, rounding error, okay? Now, what is important is that our universe right now, what we see is 10 to the degree 28 centimeters. It's a minuscule part of what we see here. So this is huge. Imagine that you have Earth with expanding radius. It will be flat and homogeneous. You take Everest, you stretch it, and you have Plato instead of Everest. That's how you explain why our universe is so uniform, by stretching everything wrong with it. What happens when you're on the surface of the Earth, you look at the surface of the Earth, it looks like flat, but not exactly. You can round it, okay? But when the Earth becomes that big, then it's just plain flat. So one of the predictions of inflationary cosmology was that the universe was flat, uniform. But then if it is flat and uniform, where did we get galaxies, which are important for our life? And the answer was given by this person, Vyacheslav Mukhanov, who was sitting next door to me in Lebedev Physical Institute, and he was talking some nonsense about quantum fluctuations creating galaxies, and then I learned this, and I've learned that with the help of inflation, that's exactly what happens. And people are, well, making experiments right now, checking it, And that is why they start believing into this story. So Planck satellite, this is a $1 billion experiment. People really trusted us a little, okay? So they look at the sky, they measure temperature of the sky in all possible directions. They find that measure of the sky is slightly different in different, well, directions. And the slight different, these spots, they were traveling all over United States, explaining it to people around, and they came to me and said, we do not understand it. We show them the picture, and nobody is excited. And I say, oh, that's very simple. I go to Home Depot, I buy 2 cans of spray, and I produce a picture, and it will cost me much less than $1 billion. So what is so special about that? The special thing is that what you do really, what the universe did, it takes these quantum fluctuations during inflation, it expanded them exponentially together with the universe, it stretched it to the photographic plate, which is all our sky. You cannot do better than that. You cannot do grander than that. And then photographed this. This is a photo of the moment of creation, 10 to the minus 35 seconds after the Big Bang. We see it right now. This is amazing. This is really stunning. But what else is interesting there? There's some distribution. Here is a blue area, which is pretty large with some small fluctuations. This is gray. Okay, so they studied distribution of this. And there is a theoretical prediction for the distribution of spots, which is shown by this green line. Okay? And each of these spots is a separate experiment for separate different wavelengths, different angle scale. Each of these experiments just feed this curve magically. Okay? Here there is some uncertainty. Uncertainty simply because we study large angles where you have one sample or 2 samples if they are smaller. So statistics is impossible to get there. But in places where everything is small, statistics is perfect, and so far so good. So people start believing that indeed inflationary theory is not just science fiction, and we seem to achieve it. We seem to reach the Einstein dream. We explain how by this huge expansion, the universe everywhere became the same by this rapid expansion. But we did it, but then we were up to surprise. Because we start thinking, well, let's start with the football, okay? Not with the red ball, but with the red and green and yellow and blue, etc. What will happen after inflation? And that was happened. And what will happen? The person living here will see only blue universe, and he will try to find a theory which explains that only blue universe is possible. The person, like me, would be born in the red universe, and he would try to explain why only red universe is possible, okay? And the size of this is really such that we cannot escape because the distance is really, really very large. So what pessimists would talk about this? If each part of the multiverse is huge, we will never see other parts, so it's impossible to prove that we live in the multiverse, right? Okay, they're so big, we never see it. Optimist, what he said. If each part of the universe is huge, we'll never see other parts, so it's impossible to disprove that we live in the multiverse. And what Einstein would said, he said, I would rather be an optimist and a fool rather than pessimist and right. Okay, so let's just watch. Let us be optimists and fools, maybe not necessarily fools. The thing that this scenario is more general than the original one. Because if you want to have a universe, you need to find a reason, a profound reason why the universe must be red or blue. And everything else is forbidden. Think about the electromagnetic spectrum. It's the same electromagnetism, but then everybody comes here with the t-shirts of different color. That is the same universe, just different parts of the spectrum. Think about water. Water can be liquid, can be solid, and can be vapor. Think about the captain of the ship who thinks that only liquid water is possible. You know historic example? Titanic, yes. So be careful insisting that water can be only liquid. And what else we learned? That even if we start with only red or only blue, then quantum fluctuations produce the universe of multicolors. Each part is exponentially large. I call this Kandinsky universe in the name of a Russian abstract painter. So this allows us to justify the anthropic principle. We live in those parts of the multiverse where we can live. But it was never easy to discuss anthropic principle, even with your friends, because it was something which everybody despised. You cannot solve the problem, so you bring this, okay? And recently, the concept of string theory landscape helped us a little bit to stand in this game. What happened is that when we started studying string theory tried to explain what is the origin of this vacuum energy of almost nothing. And then we worked and worked and worked and then found some construction. And in this construction, you found that a universe in string theory is 10-dimensional, 6 dimensions out of one time, 3 spaces, and 6 are extra. But 6 dimensions can squeeze into something small, so we cannot travel there. So we think that this is not a dimension, not a space. We have 3 dimensions, large dimensions. But depending on how they squeeze, and that's combinatorial process, how they squeeze, you have different laws of physics surrounding you in this universe right now, okay? This is a big number. So you have this number of options, and people are not so sure that this is 10 to the 500. They start counting, and they found that it may be much more. And this is the picture which illustrates what we found. This is the beginning. Here the universe just born in a stage of inflation. Yellow universe can produce red universes and blue universes. They can produce green and blue again. And so the process continues. We look at this, we think this is a Big Bang. Well, this is a pretty Big Bang. And when we're looking from here, we say this is a Big Bang. Yeah, it is a pretty Big Bang. And then these guys look here and say, no, this was the Big Bang. Yeah, this was a pretty Big Bang. Where is the Big Bang? I don't know whether there is a Big Bang. But what we know is that this process of creation of new universes continues. And why do we live in some particular parts of the universe? Because there are some parts where human beings possible, where they can live. So this brings you anthropic principle. You have a multiverse which consists of many pieces, and in some of these pieces you can live, and in some pieces you cannot. It is not that somebody created the universe for our benefit. I remember how Hawking discussed this anthropic principle and said, I would not believe that our God created the universe for the benefit of this particular kind of monkey. Okay, so no, there is no need for that, because if somebody created the universe or the universe just was born, then it continued spreading its own, reproducing itself in all of its possible ways, and in some of them we can live, and in some of them we can't. Can we test the multiverse theory? This is the question which is often asked. And the theory provides the only known explanation of many experimental results. Nobody took them like experimental results. So here is an example. You have a proton mass and a neutron mass. Proton mass is almost exactly equal to neutron mass, but no law requires it really. If proton mass, however, were 1% heavier than neutron mass, or 1% lighter than neutron mass, then there would be no either protons or neutrons, and our life would be impossible. So life would be impossible. Who cares? We are living in the universe where this is just so fine-tuned. But in multiverse, you have a possibility. Here is a universe where you have proton heavier than neutron. Well, sorry, you cannot live there. Here is another one where neutron is heavier than proton. You cannot live there. So you have a correlation between your properties and the properties of the part of the universe where you live. How about mass of the electrons, which are 2,000 times lighter than the mass of the proton? What's so special? Increases 10 times, we're dead. Decreases 10 times, we are dead. But we are in the universe where electron mass and electron charge, they are measured, they are constant in our part of the multiverse. And therefore, I will go to the authority given to us by Sherlock Holmes. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. So welcome to inflationary multiverse. Thank you.
Multiverse? Well, I just want to say that was amazing. And in all the research I did, I never once looked up Miss Universe. Just want to say. Well, welcome to Carnegie and to Coverley, and that's incredible. Andrei and I have had an opportunity to get to know one another a little bit, and I want to share his brilliance and his insight and his humanity with you here tonight. You also know about the pigeonhole questions, which you've been putting in and voting on, and I'm going to cycle through those, and then in a little bit we have microphones on either side, and those who are still willing and brave and curious can stand by, and we'll see how many questions we can get. Does that sound like a deal?
Yeah.
Good. You told me something when we first spoke, which was remarkable. One night, Andrei told me, he woke up and shook his wife, I guess, and woke her up and said, and I'm quoting you now, "I think I know how the universe was born." Now that's quite a thing to wake up to, especially since your wife is a theoretical physicist, a professor of physics at Stanford, supergravity, string theory, inflationary cosmology. What did she say to you when you said that to her?
She listened. You know, sometimes it really helps to have a wife who listens. But it helps you even more if you have a wife who understands.
Did she challenge you?
Oh, yeah.
Did she,
yeah.
Did she believe you?
At that time, I cannot say that I completely believed myself. So it took some time to grow on us.
Let's talk about the inflation theory here, and let me ask you a few questions about it. So here's how NASA describes it. The inflation theory, they say, offers solutions to problems relating to the Big Bang theory and several other open questions in cosmology. It proposes a period, which you described, of extremely rapid exponential expansion of the universe prior to the more gradual Big Bang expansion, during which time the energy density of the universe was dominated by a cosmological constant type of vacuum energy, and later decayed to produce the matter and radiation that fill the universe today. But you say it's ongoing, it's continuing.
It's a different vacuum energy. So in the early universe, expansion was enormously fast because the energy density there was enormously greater than it is now. Right now, this discovery of non-vanishing vacuum energy was astonishing. We still do not quite know whether it is vacuum energy or something which will slowly decay in the future. There are some controversial results on that subject right now. But if it is vacuum energy, then the universe will double every 10 billion years. 100 billion years later, we will have our galaxy, and there will be no other galaxies around, so we'll be lonely. We still have some time.
That's encouraging. As you know, people have put in their questions, and some have voted. The top question that has come from the audience tonight is as follows, and I'd like to ask it of you. How would scientists confirm the existence of the multiverse? Through direct observation, some other method? What ways are scientists currently working to confirm or refute this?
Okay, there is one way of really seeing this other universe. Could be that we are in one part of the universe and there is another part of the universe, and then this other part of the universe kind of expands in our direction, comes closer. Then you're going to see it. Unfortunately, this will be quite painful, though quick, Okay, because usually if there is a reason to expand, then this part of space expands onto you with a speed equal to the speed of light, and you see the wall when it hits you, and then you do not write any scientific reports after that. Okay, so that is a possibility, but not very promising. Another way of really, thinking about it, you can produce this universe in the laboratory, this bubble of the universe. There were some questions, like at CERN accelerator, they collide high-energy particles. And if we live not in the best of the worlds, then this collision can send us all to the best of the worlds. Of course, in this other world, everything was good except for there will be no us. Okay, so that was some worry about it, and therefore, no, actually there was no real danger, honestly. So it's difficult to test multiverse experimentally like that. However, there are these indirect consequences of the existence of the multiverse. They are of a conceptual nature. If we have a theory which explains many facts of our life, like smallness of this vacuum energy, which is incredibly small indeed, no scientific explanation. People were trying to build a theory explaining why it must be zero, why the energy of vacuum must be zero. They all failed, okay? But now it is so miserably small. What is the reason it is being close to zero but not zero? And the only reason, if it were 100 times more, we will be dead, because this expansion will tear apart the galaxy. If it were negative, we would be dead because the universe will rapidly collapse. So all of this kind of thinking is possible only if you have a conceptual framework for that. And therefore, we are not proving that this version of multiverse, that version of multiverse, we are suggesting this is a framework in which metaphysical questions can become physical. So I think that this is a progress.
You and I talked about this too, that the theory of relativity says that nothing can move faster than the speed of light, right?
Yeah.
So how is it that the universe was expanding faster than the speed of light?
By not moving, by expanding. Okay, so here, what special theory of relativity tells you? Suppose you have a membrane, okay? You pinched it, there is a wave. This wave cannot propagate the signal, cannot propagate faster than speed of light. Then suppose you have a membrane and it expands, our universe expands. This galaxy here and this galaxy here. Right now, some galaxies are moving away from us with a speed faster than speed of light. There is nothing contradicting special theory of relativity. It is a consequence of general theory of relativity. It is stretching of space. It's not a motion of bodies. Galaxies do not move. Galaxies stay, but the distance between them grows.
Another question that got a lot of votes in this room, if you're thinking about these different structures, what would the boundaries between two universes be like?
Yeah, that's partially I just answered. If you have another universe and it goes to you, go fast away, okay? If it goes away from you, you may try to catch up, but it's almost hopeless. However, there are some versions of this scenario where there is no rigid boundaries. It just fields, something which determine properties of our universe, slowly changing from point to point. So in one part of the universe, you will have great amount of dark matter. In another part of the universe, you have small amount of dark matter. And these properties will slowly change, modulated over our universe. So there are some harmless part of the multiverse, and there are some dangerous part of the multiverse. And we can live only near the harmless part.
You talk about people who've raised questions about this. So George Ellis, Emeritus Professor of Complex Systems at the University of Cape Town, who wrote with Stephen Hawking nearly 50 years ago, The Large-Scale Structure of Space-Time, wrote a few years back that, sure, the multiverse can be out there, way over the cosmological horizon, but so far over the cosmological horizon that we'll never find it. And he writes the following: In looking at this concept, we need an open mind, though not too open. It is a delicate path to tread. Parallel universes may or may not exist. The case is unproved. We're going to have to live with that uncertainty. Nothing is wrong with scientifically based philosophical speculation, which is what multiverse proposals are, but we should name it for what it is. Yeah. Scientifically based philosophical speculation?
Which is okay, but if you have a speculation which is the only speculation which allows you to solve several scientific problems, so I will go with a name. I don't care how you call it. It's just whether it's helpful or not. You know, the problem with all of this naming and stuff, sometimes you know that we were born with some set of ideas which is common to our community, our society, our history. The whole concept of expansion of the universe was so foreign to Einstein that he insisted that this is nonsense, so that this solution, which was put forward by Friedman, cannot be right, etc. It was just psychologically difficult to accept, except for in Indian culture, this would be fine, okay? Universe is born, universe died, normal part. So you need to be a little bit more open to possibilities than many people usually are. And I'm sure that I'm closet to many possibilities, and I do not even see the places where I'm closet, because people who are used to something, they do not see the boundaries.
As you develop this and publish this, this work, how much have you been second-guessed and challenged and questioned? And was that difficult?
Well, to tell you the truth, not really. Because if you're really sure about what you're saying, then it's kind of a pity that it is not seen by others. But it is difficult and upsetting in the sense that if you would allow yourself to be a little bit more open, you see it, then you will become enriched. But then because you decided to be so closed, then you are, robbing yourself of some beautiful possibilities. So but yeah, it is kind of a pity when I remember how I was invited to give a talk at some very famous scientific organization, and I told them that I'm going to talk about anthropic principle, or I can tell about something simpler but not controversial. And they told me, you better talk about something else, because we used to throw eggs to those who talk about anthropic principle. So I came there, the first part of the talk, I gave a dull, normal talk. The second, I said, okay, now I hope that you did not have enough time to go to Safeway to buy eggs, so let me continue. So it is hard, it is changing.
Let me ask a few more questions from the audience, the good ones, and we'll keep them fairly short because then we'll go to the mics in a few minutes. Another popular question, what came before the Big Bang?
That's a real question. Okay, that's a real question. If I would know the answer, I would start my lecture with this, okay? The answers to this question, what we know is that it is probably easier to answer this question using inflationary theory, because you do not need much to create everything. So if something could come from whatever was before and this something can inflate, you can do it, okay? Unfortunately, it's really difficult to go from something pre-existing to something which appears right now. It's not a theorem that it is impossible. Many people tried, many people failed. Many people who tried and failed continue insisting that they did not make a mistake, and that is sad, okay? But it is a really challenging thing. What I can tell you, though, that it might be that we are asking question incorrectly. because we're asking questions about what was at the time when there was no universe. I think that it was Saint Augustine who answered this question, and he have written something like that. I am trying to remember something like that. I will not answer you merrily that at that time God was preparing hell for those who ask such questions. No, instead of that, I should answer you that there was no such time when God was doing nothing. No such time. So the question was there time? What is time? Sorry. Okay. Well, everybody knows what is time, right? Oh, excuse me. I'm going to talk about quantum cosmology. Quantum cosmology is much, much more complicated than everything I told before, okay? Bryce DeWitt, famous, wonderful genius, whose papers nobody was able to read because they were so far ahead of time. He have written his paper about 200 pages, sent it to physical review. It was only refereeing for a year because nobody was able to read it. And then a year later, they told him, okay, we'll accept it if you cut it into pieces, 3 pieces. He cut it in 3 pieces, they were accepted. One of the pieces was about quantum cosmology. In this quantum cosmology piece, he derived equations for the wave function of the universe. So what is wave function? In quantum mechanics, if you know a wave function, you take a square of it, you give a probability of what is going to happen, okay? So it's a necessary tool. Wave function for the universe, equation for that, that's what he studied. Normal equation for wave function in quantum mechanics is like that. Speed of the change of the wave function is proportional to energy multiplied by a wave function. He looked at it, he said, oh, but we know, and I told you about it at the beginning, remember, that the total energy of the universe is exactly equal to 0. So, speed of the change of the wave function of the universe is equal to 0, which means that the wave function of the universe does not change, which means that nothing changes. I'm talking right now, you see something changing, you're probably going to remember something, but according to this theorem, nothing can change. And the Bryce DeWitt, proving this theorem, he told us that actually we never ask a question about the evolution of the universe and the wave function of everything. We cut ourselves out of it, okay? And then we look at everything else, and everything else has energy such that energy of this plus my energy, which is E equal to mc squared, okay, huge, okay? These 2 energies together give you 0, but means that everything else has energy equal to minus my colossal energy. So wave function of everything else changes with respect to, time on my clock. Evolution of the universe is relative. Without an observer, the meaning of evolution is questionable. And when I tell it to you, I'm just all shaking and trembling because it looks so much like solipsism. One of my friends, he was the famous astronomer who studied expansion of the universe, Hubble constant, etc. And while discussing with him, he told me, oh yeah, I like the idea, Actually, I was a solipsist in my youth. And then once I met another guy in the bar, we were sitting and started talking, and he told me, oh yeah, you are also a solipsist. There are not so many of us. But according to the solipsist, it is the only one at all existence. So all of this is really tricky, philosophically challenging. I'm just telling you that when we're talking about time, you should really define the concept precisely. And for the universe as a whole, there may be no time when it emerged. You should use something else there. And I know how dangerous it is. I would continue with the story, but I better stop.
All right. Let me do one or two more questions from here. If you have a question, we don't have a lot of time, make your way to one of the mics. I'm going to ask you, when we get to you, to be very brief with your question, and you can be brief with your replies, and we get as many in as we can. But I did want to ask this because I think it's totally fascinating and completely relevant to other things you've been talking about. It is an audience question as well, and it is as follows. Are physical laws the same between multiverses, or are there variations that could still be stable?
We studied a primitive version of the theory of the multiverse, where you have one overwhelming law, like string theory, with different compactification. You have the same fundamental physical law, like you have written string theory, and then you study consequences. And in different parts of the universe, you have just like different phases. It's like you have the same Earth, but here is China, here is Russia, here is the United States, different countries with different laws. Okay? If they were very, very different, they would not know about the existence of each other. So it's the same people, but different realizations. Okay? So that's a possibility. But another possibility is that the laws by themselves, and this coupling constant, but not only coupling constant, but quantum mechanics, it may be something else which is built from more fundamental blocks. And this is going along with some ideas which were developed by John Wheeler a long time ago, who was talking about it from bit. We still do not know deep answers to these questions, and we would be happy to work on them. But we start with the simple, and I told you today the simple story.
Question.
Yeah, thank you very much. We do everything from a human perspective, but this overall is not really an efficient use of energy. I mean, there's got to be a better way to get a brain going. But my question is this. How differentiation, in other words, why is it assumed that beyond, there is any differentiation? In other words, maybe differentiation is the exception, and overall entropy will just...
Yeah, okay. So the answer was this part which inflationary cosmology, the normal one before multiverse, was proud to provide. We start with the red or with the blue, and then it blows up, and whenever we look, much greater than the speed of light multiplied by the age of the universe. Much greater. It's everywhere blue. Go further, it's still everywhere blue. And then later, you will find something red. But you cannot go there, because you have only these 10 billion years or 14 billion years. Walking or even sending light will not bring you there. So what we see is uniform because of rapid stage of inflation.
Yes, I wonder if you could comment on the all-sky images of the cosmic microwave background radiation that seems to show temperature concentrations that some cosmologists have indicated they feel might be contact points between multiple universes.
Yeah, it is possible that we have just on the boundary of our visibility some seeds of expanding which may move to our part, but they're still not close, far away. And we can see these imprints very, very far away from us, some special modification, some asymmetry because of this. It is possible, okay? Probability of that, because we do not really know all details of the story, we cannot calculate probability in a sufficiently convincing way to us, because it depends really on the details of inflationary theory, does not look very plausible, because if they are really at the distance, natural scale, which I would get from the constants which usually appear in the theories which we study, then they would be exponentially far away from us. But theoretically, it's not impossible. So it's possible to check it just in case. We are doing measurements anyway. So if we see some anomalies, we can always study whether there is something anomalous which fit the bill.
Thank you.
Go ahead.
On the anthropic principle, would you agree that there might be other universes which don't have the fine structure constant to make life as we know it, but there could be some other strange form of intelligence and life, and they would be wondering why the universe just had those values instead of our values?
Yeah, absolutely. Because when we are thinking about, well, life, usually we are thinking about carbon-based life, right? Okay. Just imagine the same discussion in a very similar auditorium, even here on Earth, 1,000 years later, where carbon-based life will be discussed by some, robots sitting around and saying, shall we, silicon-based life, think about this carbon-based life? Was it necessary for evolution, or it was just a passing interval? Yeah, so one should be really not very chauvinistic about our own, place in the universe. And the thing that will really help us to understand it, but this is really something which I would really hope that sometimes in the future will be done. Will people really more seriously think about what does it mean consciousness? What does it mean life? Whether my iMac suffers when I turn it off or it just beeps. I take this question really seriously.
I'm afraid we're out of time here for questions from the floor because we need to let you get on to your reception. But the last question I want to ask you, Andrei, is where is your research heading? Where is this field heading now? What are you working on at this time?
Well, the research field, I can do multiverse in spare time, but we first must also prove that the general concept of inflationary cosmology does well. And there are many confirmations of it, but which version of inflationary cosmology? Which one? Okay. So right now, more and more experiments are in planning. Several already finished their work. They are giving us incredible amount of information. I can compare what happens right now, and maybe this is a good point to stop. I can compare this age where we're living right now with the era of great geographic discoveries. You know, map of the Earth was written once. It was later, something.
There you go, you're
here.
back.
Yeah. It was later redrawn, and right now you just, use your iPhone to find the next restaurant, so geography is over, okay? However, with cosmology, until very recently, just 100 years ago, we did not know that a single galaxy except ours exists. People really debated it. Cosmologists, very, very clever people, they debated it. And then they found that not only they exist, but they are moving away from us. And they counted the number of galaxies, and they found that there are 100 billions of galaxies in our part of the universe only. And then our astronomical devices put it to the verge of the universe right now. We can see all the way towards this, the boundary, which is the speed of light multiplied by the age of the universe. Actually, we can do 3 times more. Okay, but that's because some things which send us light, they are at a greater distance right now when they send the light. So we can see a little bit more than speed of light multiplied by age of the universe. But then that is a limit, okay? So this is our universe, and next million years, the age of the universe will be 14 billion plus 1 million, nothing, okay? So we will see the same thing. And now we are at the stage when we are mapping the universe, and we are producing a map of the universe, which is not going to change in the textbook written in the next million years. That is something. If you think about astronomers, they live the best time of their life. You think about it from the point of view of probability, of anthropic principle. Universe had 14 billion years to look at itself, but it did not have good eyes, telescopes. He did not have good brains, astronomers. Now everything is in abundance. During the last 100 years only, our universe was able to look at itself in the mirror and study itself. This process will be over in another 50 years. So it is like 150 years compared with 14 billion years. It's nothing. What is the chance that we live in the time where we're so lucky that our universe is so lucky that by looking by our eyes on itself, the universe can recognize itself in all its grandeur. So we live at that time. It's magic that we are allowed to do it. Thank you.
And I would say that it's magic, and we are lucky that you lived in this time to help us hold up this mirror and help us see this.
Thank you.
Ladies and gentlemen, please join me in thanking Andrei Linde.
Thank you.
That's great.
Thank you. We can disarm ourselves.
Great.